Hello, with this video we begin chapter 18 of Young and Friedman's University Physics. This is a chapter on the thermal properties of matter. And this first section is called Equations of State. And equations of state has to do with various equations that relate to the state of matter in terms of its volume and its pressure and those sorts of things. These sorts of variables, pressure, volume, are called state variables. So variables that describe the state of a material are called state variables, its pressure, its volume, and so forth. And then equations that relate to these states are called equations of state. And of course, the main equation for this section is the ideal gas equation. And it's interesting if you compare this chapter with a chemistry textbook, for example. I have chemistry videos as well as physics videos, and you'll find that those chemistry videos kind of cover the same territory, but in a longer stretch of videos. So like there's a whole chapter in the chemistry textbook on gases and so forth. Well, you may know the ideal gas equation, and it relates to a number of principles that were put together, I think, largely in the 1800s. So we know that the volume of gas is proportional to the number of moles of gas. Gases aren't like solids that can be more or less dense. They're not as much like that. They tend to fill a space in a more regular way, shall we say. And so the volume of gas is proportional to the number of moles of gas in a particular space. That's one principle. Volume is inversely proportional to pressure. That makes sense because when you pressurize something, the volume decreases. And if you have less pressure, the volume expands. Or, if you have a bigger volume, the molecules expand out and there's less pressure. If you have a smaller volume, the molecules are bumping into each other more and you have a higher pressure. So all this kind of makes sense. And then pressure is proportional to temperature as well. When the temperature goes up, the excitement of the molecules go up. And so they bounce into each other more. And so there's more pressure. But if the pressure goes down, then the molecules are moving more slowly and they run into each other less and there's less pressure. All of this is kind of common sense once you understand the way molecules work. And therefore, we have the ideal gas equation, which is pressure times volume equals the number of moles of molecules times a constant times the temperature. This ideal PV equals nRT. This formula embodies the principles that we've just said. So pressure and volume are inversely proportional. And so as the pressure goes up, the volume goes down at a constant temperature. Because if you have a constant temperature, then nRT is a constant. And so that means that if the pressure goes up, the volume has to go down. And if the volume goes up, the pressure has to go down in order to keep this constant. So at a constant temperature, PV, have exactly an inversely proportional relationship. Whereas pressure and temperature are proportional. And that means that as the temperature goes up, then the pressure has to go up for these two sides to stay equal. And of course, the volume is proportional to the number of moles of the molecule. And so if the volume goes up, the number of moles assumably has gone up as well. So this all makes perfect sense. It is the ideal gas equation. Okay, and of course, I will have chemistry videos on this as well, following the gas chapter of the chemistry textbook. So this assumes absolute pressure and absolute temperature. So temperature here is in kelvins, and pressure assumes so there's absolute pressure and there's gauge pressure. Gauge pressure is the pressure in relationship to the atmosphere. Absolute pressure is the pressure it would have in a vacuum. So these are the two assumptions of the values that are being used in the ideal gas equation. And what is R? The constant R. So this is a fun little thing that at some point the chemists and physicists of the 1800s, 1700s discovered that when you have these proportional relationships, like this, that all you need to get from a kind of general proportionality to exactness is a constant. You find that out by doing experimentation. So you know that PV is proportional to NT. But how do you get from it being proportional to it being equal? Well, it's a constant because they're proportional. That's the nature of a constant, of something that's proportional. And so then you do experiments and you discover that R is 8.31 joules per mole Kelvin. Okay, again, remember that it's absolute temperature, it's in Kelvin. Okay, the ideal gas equation. You've got this section. Now there are some other details in this chapter, in this section of the chapter on equations of state. So the total mass, M total, the total mass equals the number of moles times what's called the molar mass. Now here again, see my chemistry videos because this particular section of the physics chapter condenses what is a number of concepts in chemistry. So if this seems, wow, there's a lot of stuff in this chapter I've never heard of before, you go back to your chemistry or go take chemistry or go watch some chemistry videos. So the molar mass is the number of grams per mole that is true for a particular element or molecule. Now, you may have never heard of a mole. In fact, here I am talking about moles, and you're like, what? Those little things that peek their head up in the ground? Whack-a-mole? What is going on here? I thought this was a physics video, not a zoology video. And I'm sorry, I should have explained what a mole was. What is a mole? A mole is basically a way of talking about massive numbers of atoms and molecules. So atoms and molecules are really small. They're really, really small. And so we don't use the actual number of atoms or the actual number of molecules as if we could count them down to the actual number anyway. But there was a guy named Avogadro who basically estimated the number of atoms, number of carbon atoms in a gram, and on the assumption that a carbon atom has 12 protons in its nucleus, because that's the atomic number of carbon, 12. He basically set a standard for what he called a mole of a substance. And basically a mole of a substance is 6 times 10 to the 23rd power number of something. So a mole of atoms is 6 times 10 to the 23rd power of that atom. Or a mole of molecules is 6 times 10 to the 23rd number of that molecule. So the molar mass is the number of grams there are for a mole of a particular thing. And so grams per mole. So if you have a mole of carbon, you have 6 times 10 to the 23rd power carbon atoms. And so the molar mass is the number of grams there are. It turns out to be 12, by the way. A mole of carbon is 12 grams of mass. So the molar mass is the grams per mole. And if you multiply grams per mole times the number of moles, you get grams. Ta-da! By canceling out. So since the total mass equals the number of moles times the molar mass, then we can go back to the PV equals nRT formula and substitute in M over M for N, right? So if M total equals NM, then if you divide both sides by the molar mass, you get M total over M equals N. So I've just substituted that in. So now we have another formula that we might use in a different kind of situation. Here's another variation on a theme. So the density is the volume per mass, right? And so if I subtract both sides by M total, then I have volume over M total equals rho, the density. Then if I divide both sides by P, okay, I've done something wrong here. I'm sorry, it's mass per volume. Beep, 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 beep. Density is mass per volume. So if I divide both sides by V, then I have mass total over V on this side, which is rho. and then multiply both sides by the molar mass, and I get PM, which is right there. And then I get this on this side by dividing by RT. And so there is the density. The mass per volume, the density rho, equals the pressure times the molar mass divided by the R constant times the temperature. Okay, all we've done is we've shuffled. We've used algebra to shuffle the components around in order to have a formula for something else. Okay, with constant mass, so if we have constant mass, PV equals nRT, or let's take this one here. With a constant mass, then this is constant, and this is constant, and R is constant. So if I divide by T, then PV divided by T equals a constant. And that's going to be true no matter what PV over T is, right? And so we have this equation that for any PV over T, it's going to equal any other PV over T. These numbers are going to adjust themselves in order for this to be equal. So if you increase the pressure, then the volume is going to have to go down, or the temperature is going to have to go, what did I say? Increase the pressure. If you increase the pressure, then you're either going to have to increase the temperature, or you're going to have to decrease the volume in order for it to remain constant. So some interesting variations upon the PV equals nRT equation here. Standard temperature pressure. Okay, you often see STP in chemistry and physics problems. STP stands for standard temperature and pressure. So standard temperature and pressure basically is on the 0 degrees Celsius is the standard temperature. So if you say this is what it is at standard temperature, you mean this is what it is at 0 degrees Celsius, which of course is 2.73 Kelvin roughly. So that's standard temperature. Standard pressure is 1 atmosphere. That's allegedly the pressure at sea level, which is 1 times 10 to the 5th power pascals. So these are the standard temperature. This is the standard temperature, this is standard pressure. And so all gases, a mole of any gas will take up 22.4 liters at standard temperature and pressure. Okay, now we get, now the last part of this video, we're getting to some of the details that are a little bit more complicated. I think everything we've done so far is really not that difficult. It's just shuffling things around and some basic common sense, things that make sense, really. Now we're going to get into a little more complication. So this is the van der Waals equation. Van der Waals was a Dutch scientist who recognized that at high pressures especially, the ideal gas equation doesn't really work, PV equals nRT. It doesn't work for 2 basic reasons. First of all, the molecules themselves, or the atoms themselves, take up volume. And so the volume is not entirely accurate. You don't have as much space, actually, as an ideal gas is thought of as kind of like a point, as not having any volume. It's a theoretical concept, and it doesn't really exist, right? And so in the real world, the molecules that are in the space decrease the volume because they take up some of the volume. And so van der Waals introduced this, the ideal volume, but you have to subtract the number of moles of the molecules times a constant B. And you have to decide, you have to experimentally determine what A and B are in this equation. It's going to be different for each particular substance. But basically, by subtracting the number of moles times this constant, you're going to come up with a more accurate sense of how much volume is actually in play, because some of the volume is decreased by the presence of the molecules. Okay, so van der Waals adjusted the V part of the equation by subtracting the volume of the molecules themselves. So that's one thing that had to be adjusted. The other thing that has to be adjusted is that the pressure is offset a little bit by the attractive forces of the molecules themselves. The molecules are attracting themselves a little bit, which decreases the pressure. So to get from, so the pressure decreases. So to get from the actual pressure to the pressure in an ideal situation, because the pressure decreases, you have to add a little bit to account for the decrease in pressure from the attractive between the forces. And as it turns out, the decrease in pressure is proportional to the square of the number of molecules per volume. And the way that Young and Friedman explain this square is they say there's basically a layer, there's a layer of molecules near the wall of the container, and then there's a layer of molecules beyond the container, and so you always have a squared situation that is decreasing the pressure as all of these times all of, it's proportional to these, and it's proportional to these, and if it's proportional to both of them, then it's proportional to the number of them squared over the volume of them squared. Well, whether that makes sense or not to you, that is the amount that roughly the pressures decrease. So to get back to the ideal pressure, we've got to add that number in to get to nRT. So this is the van der Waals equation. It is not perfect, but it's amazing what they were able to do in the 1800s, just using some basic principles of common sense like that. That's fun. So the van der Waals equation. So the P part accounts for molecular attraction, and then the V part takes into account the volume of the molecules themselves. There you are, van der Waals. Okay, another thing in this chapter are PV, pressure volume diagrams. So here is an example of an isotherm. Iso means same, therm means temperature. So at the same temperature, for an ideal gas, you have this nice little curve that as the volume increases, the pressure decreases. So pressure's decreasing because the volume's increasing. Or as the pressure increases, the volume decreases. So you have a nice little isotherm, a diagram that tells you how the pressure and volume for this particular ideal gas, actually maybe for all ideal gases, how it works at a particular temperature. Now, as it turns out, we don't have ideal gases, right? And so in the real world, you have as long as the temperature is high enough, it works like an ideal gas. But there's a critical temperature, a TC, and below this critical temperature, you don't have it in a gas form at certain pressures. So when the volume when the pressure hits this point, as the pressure decreases, and it shouldn't go backwards, by the way, I'm a bad artist in this particular case. So when it hits a particular pressure, it will stay at the same temperature until it gets to a certain volume, and then the pressure will continue to decrease. And in this kind of spot, it's in a kind of liquid vapor equilibrium. So it's not in a gas, it's not in a pure gas form, and the pressure remains constant as it's in this particular expansion of volume. So this is a PV diagram for something that's not an ideal gas below a certain critical temperature. Okay? Last thing, this section began with a state equation for solids, which I thought pedagogically wasn't an ideal thing. Why start off with one of the more complicated equations at the beginning of the chapter? That didn't make any sense to me, but here it is. And so this is a state equation for solids, because even though they don't expand and contract as much, solids do expand and contract with temperature. And so the volume of a particular solid is going to equal to its initial volume. So we're having a change of state because of changes in pressure or temperature. And so the resulting volume is going to equal the initial volume times this gobbledygook, 1 plus So B is the coefficient of volume expansion, beta, it's beta, sorry. This beta is the coefficient of volume expansion. And this goes back to chapter 17, and this is the change of, this relates to the change in relation to a change in temperature. And you can see that it's coupled with temperature. The new temperature minus the initial temperature, and so if there is no change in temperature, then this is zero and this drops out. But if there's a change of temperature, then this coefficient of volume expansion is going to affect the volume. And then minus the, this is the compressibility coefficient, constant, that is the compressibility constant, which relates to the change in volume in relation to pressure. And so here you have pressure, the resultant pressure minus the initial pressure. And so if there's no change in pressure, again, this is zero and it drops out. And then you just have, so if there was no change in temperature and there's no change in pressure, this goes to zero, this goes to zero, and it's basically 1 times the initial volume. Ta-da, the volume's the same. But, and so this is for solids again. This is not, we're talking about gases now, we're talking about solids. And so, but if there is a change in temperature, or if there is a change in pressure, or if there's both a change in temperature and a change in pressure, then in accompaniment with these particular coefficients, the volume is going to change similarly. So there you have it, the state equation for solids to round out this somewhat involved section, right? We've put a lot in here. There's a lot of chapters of chemistry in this one little video. But as I've said, B is the coefficient of volume expansion, and K is the compressivity, sorry. Okay, we are done with this video. Let it be so. On to the next section of chapter 18 of Young and Friedman's University Physics.